All right. So, WebCrack plus FPGAs plus matrix-like effects and processing power, times Ninja equals performance comparisons, because we're obsessed with numbers. So inside, JC WebCrack, what are we getting, right? On a PC, 1.25 gigahertz, 150,000 keys a second, right? 1.25 gigahertz G4, right, basically. And a P4, 3.6 gigahertz P4, about twice that, 300,000 keys a second, right? On an FPGA, as we just said, basically Pico WebCrack on an LX25, which again is these compact flash, this particular compact flash kind of chip, running, what, 15 of these?
Well, that's for one of them, and that's 15.
This is for one, right? So for a single LX25 is 9 million per second. For a cluster of 15 a la the Green Beast, 135 million keys per second, right? 135 million keys per second. So in 60 seconds, 135 million times 60 is really a lot, right? So in a minute, you could do essentially over a half a billion, right? Essentially. And then an FX60, is this an FX60?
Yeah.
So in one FX60, as opposed to an LX25. So LX25, FX60, right? 18 million. So twice this, essentially, right? Per second. So.
Oh, yeah.
All right. So now we'll totally switch gears and get off the whole matrix thing, only because I don't have any more cool videos. If we have time, actually, I have other things I can show. But who here remembers a thing called deep crack? Excellent. All right. So deep crack, for people who don't know or aren't sure, the slide sort of allocates things. I'm just going to go down this. Deep crack was a project that was initially sort of dreamt up and commissioned by John Gilmore and the EFF, the Electronic Frontier Foundation. And as a disclosure, as an item of disclosure, I have to announce that I worked for the EFF a couple years ago as a staff technologist. I'm no longer there, but they're all very good friends of mine. In 1998, for a number of reasons, one being that the US government was still saying DES was secure for certain kinds of classified information, not classified information, but for certain types of classifications of information, DES was still an approachable option. And vendors also were saying the same thing. Vendors were happy to sell you DES in forms that you could use and call it secure. And so, of course, there were all these different DES challenges. There was DES Challenge, which was the first one, I believe, in '97, which was broke by Matt Curtin and his team. There was also an RSA challenge, or a number of RSA challenges. Most people remember these because of distributed.net. Who remembers distributed.net? Who still runs like an RC4 client or whatever it is? Anybody? A couple people? Holdouts. I mean, just get one of these, right? And call it done, right? Go on with your day. Make a better cup of coffee, right? Do something else. RC4 is dead. So in an attempt to try to kick everybody into action, same as the rest of the talks here have been talking about exploits and vulnerabilities, and the same deal is the ability to actually throw money at hardware and make it just happen, right? So John Gilmore, the EFF, put together a project to build essentially a affordable, quote unquote, desk cracking machine, right? So when we say affordable, what do we mean? Now keep in mind, this is 1998. It's 2006 now, it's 1998, so it's about 8 years, right? We're just shy of a 10-year mark, okay? In 1998 dollars, notably more valued than now, they budgeted for around $250,000, and they spent about $210,000. I have varying numbers. One another number says they spent about $180,000 and they budgeted for $210,000. But regardless, right, we're talking around $200,000, right? $200,000 got you a machine, essentially, at the end of the day, that would crack the 56-bit desk challenge that RSA put out in essentially 4 days, average time, right? So what does $1998 mean today? Well, I did a little math, and so $10,000 runs up to about $243,000 and change. And $250,000 is the total budget. If we were as lucky as they were to not go over budget and actually go under budget, it's about $289,000. So let's just round up because I'm gonna have to go to conferences, I'm gonna have to buy people beers, etc. Call it 300 grand, right? $300,000 to do this, right? But because it's been 8 years, you get more for your money, right? Moore's law is in effect, if ever it was. And so you're not going to get the same exact hardware, even with the same ASIC design, even with the same VHDL or Verilog that you would write for the core, you're not going to get as bad performance because obviously FPGAs have evolved, ASIC manufacturing, fabrication has evolved, processes are smaller, right? We're talking about 0.13 to 0.09 process is approachable. So what did they build? Well, they built this. They built a machine, essentially, they used ASICs. We're using FPGAs, we're using reprogrammable hardware, right? They built ASICs, meaning they came up with a design and they had somebody fabricate them chips, right? They sent it to a fab, it was etched on silicon and built into a die and put on a board, right? They built essentially one custom ASIC design and they just replicated it. So they have essentially 1,536 custom desk cracking chips. Each chip is identical, they are exactly the same. There's no difference between one chip or the other, right? But there are 1,500 and change of them in a machine, okay? And then they built it in essentially two chassis. Who remembers like VME as a backplane? Like VME bus, a couple people in the back. Okay, so they basically took two Sun 2s, right, with a huge VME backplane and just built boards that plug into VME. They didn't use any of the electrics. They rewired the electrics and everything else. They weren't using like the protocols, but they were using VME backplanes to build these huge monstrous boards. Each board had 64 chips, right? So 64 of these custom ASICs. They had 12 boards per chassis, and they had two chassis, so two gigantic Sun 2 chassis, basically, right? That was deep crack, okay? Each chip, of which, again, they have over 1,500 of, has 24 what they call search units. And the search unit is essentially the logic implemented to search through the key space, right? Both chassis, with all sets of boards, all chips up and running, some of the chips notably were there for failure, right? There was some fault tolerance built into the system. If a chip burnt out or got a short, whatever else, there was some amount of coverage there. But both chassis running simultaneously at full throttle will essentially, on average, crack a 56-bit desk key in 4.5 days, right? In 1998, almost 10 years ago, right? And EFF did us the favor of documenting the whole thing in a book, right? They laid out all of the source code that they used. In this case, they laid out all the VHDL source code. VHDL is one of two popular hardware design languages. There's Verilog, there's VHDL, right? They happen to use VHDL. I happen to write VHDL. David happens to write Verilog. I say tomato, he says tomato, etc. But basically, they laid out all the code. They also laid out all of the board diagrams. So you could replicate everything you wanted with this book. And they also gave you source code, which they pulled from the PGP project back in the bad old days when sending PGP across the internet was a bad thing and people printed it out in books to scan in Europe. They included source code that you could scan yourself, verify the scan was correct, and then use it to verify the scan of every other page in the book which had the source code. And they called this book, appropriately enough, Cracking Desks, right? I have a copy of this book with me. I forgot to bring it down to the talk, and it was sort of going to be my physical prop for this piece. But this is essentially a screenshot of the book, right? This is the book. Who has this book, out of curiosity? Does anybody have it in the room? Sweet. Have you read it? Have you paged through it? I mean, even if you don't necessarily all understand it, So, me being low rent, right? I mean, David on the high end of the FPGA hacking spectrum, and me being like, random garage guy, I started saying to myself, well, I have an interest in FPGAs generally, and I have an interest in crypto, so let's combine the two. But I can't afford to sort of build, fabricate, and manufacture and sell things like this monstrous green beast, which is a huge value, actually, here in the market. But what I can afford is like little tinkery stuff, right, that I can get, over the web, basically, right? And so I started asking myself the question, well, what would happen if you just took advantage of like 8 years of Moore's Law in not necessarily CPUs, but in FPGAs? Now, it's kind of weird because FPGAs don't have a core, right? You create a core for them. There isn't, Moore's Law says that, what is it, microprocessors, or no, it's actually like transistors, right? Yeah. Transistor count will double every 18 months, right? Now, so FPGAs essentially have a bunch of logic, which you could arguably call is essentially just complicated transistor layout, right? Now, it's reconfigurable, so you have a certain amount of stuff that you can play with, right? So I was curious to answer the question was, well, I don't have $200,000, even in $1998 or in $2006, right? There's no way I can approach that, right? But what I do have is a couple $100 laying around every now and then to play with interesting projects. What I also have is an interest in learning how to do this stuff at a small scale so that it's approachable to more than just me and people who have lots of cash, right? That was really the idea behind the EFF project. I mean, $200,000 is a lot of money, but not to a government, which is what they were trying to prove, right? A government can easily build this thing for less than it cost them, because they had to hire contractors, they had to hire specialists. A government can just say, you work on this, break this thing, you get paid nothing, right? And it gets done, right? Some people in the audience have personal experience with this particular way of working. So, I want to use FPGAs, and I want to try and do as well as EFF did 8 years ago, basically, right? And I'm kind of using the fact that it's 8 years, and it might take me till 10 years to get there. So I'm kind of padding my time budget by having a lot less money. So we set out some random numbers, like some random just scattershot numbers as metrics. If I only use a total of $10,000, and I use cheaper hardware, I'm not going to be able to fabricate ASICs. I don't have the money, the budget, the time, anything to fabricate ASICs. I can't make custom silicon. What I can do is buy commercial, off-the-shelf FPGAs, okay? FPGAs are a lot slower than ASICs, lots slower. Faster than CPUs, which are general processors, but lots slower than ASICs. But obviously, FPGA design is getting better and better all the time. And people use FPGAs in the ASIC industry to simulate cores that they then go fabricate. Right? So the FPGAs are essentially like the scratch pad of the ASIC industry. Right? It's easy to implement stuff in FPGAs, and then once you've got it right, you can turn up the fab and spend $3 million in Germany in an Infineon lab building RAM or whatever. And then what I want to do is what I call shoestring parallelism. Right? Getting a bunch of boards with simple FPGAs that cost like $100 a pop, like in the board, not like individually. And then just linking them together and making the design such that it's easy to do, right? It's not quite as distributed as, say, a distributed.NET, but there's no reason you couldn't do that also. But what I want to do is build essentially a shoebox of little boards that can essentially try to crack desks in a reasonable amount of time with $10,000. So, does it work? We're not sure yet. As a point of reference, to point out where's my, there.
Yeah,
so David has gracefully displayed the board. I'm going to hold this up. This is the board I'm talking about. And this is the board that I'm currently using. And actually, when I say that, I mean this board literally is the board I'm currently using. This is a small board made by a company called Digilent. They're available on the web, digilentinc.com. They are one of a number of people who sell essentially boards, development boards, and hobbyist boards for people to play with. This is like, this board costs about $150 off the web. And so as a reference point, can most people see this? I mean, there's not a lot of people in the room, so people can probably see it. So this board, as opposed to this kind of design, which takes both skill and money, which I have neither of, this I buy for $150, and I get essentially, this is a Spartan 3 FPGA, this little bit right here. The laser pointer may be visible, but basically this little bit right here is the FPGA. The rest of it essentially is just a board with a bunch of I/O and a bunch of, it's very well labeled. So if people have ever looked at hardware and they try to figure out what it does and like hack it, this is very well labeled. It's meant to be hacked. It's a development board, it's a test board, it's an educational board. It's used in a lot of college courses. And it has a ton of I/O. And when I say I/O, I don't only mean these ports, which take little modules that you can buy off their website. We have some that just plug into these little ports and basically offer up a USB or an Ethernet port. It also has VGA and serial. It also has PS2. It has 8 switches, toggle switches, 4 momentary switches, and a few other things, right? It also has some RAM on the back to store images and the like, and it has some other platform flash for boot up code and whatnot, right? So essentially, it's a board you can play with, right? It's really easy to play with, and notably, this is not to say that the other hardware here, like these, are not to be able to play with. You can play with these. And frankly, if you come from a software development background where you just really want to write code and have it compile and do something, the closest you get to that is something like this from David, right? This is more of your like bedroom hacker, HP garage.